All right, today we're going to be looking at the derivatives of sine x and cos x, but here is just some kind of refresher skills, some things we need to remember from previous grade. So the primary trig ratios and the reciprocal trig ratios and what they're equal to, that will come in to help later on. So when we need to simplify things, sometimes taking it from secant to 1 over cos can actually help a lot. Our special triangles, so if you remember those, pi over 4, pi over 4, for a 45 degree triangle, and then our 30-60 or pi over 6, pi over 3 triangles. We'll be talking about, again, terminal arms, so angle in a standard position. The cast rule, when things can be positive and when things can be negative. So you just kind of write cast out starting in the bottom right hand, going counterclockwise, and that tells you cos can be positive in the bottom right. And then the top right, all of them are positive. Top left sine is positive. Bottom right tan is positive. The rest could be negatives. So coterminal arms. So once you have your terminal arm, you can actually get other versions of that, just kind of by going around to different ways to get to that angle. So again, you could start at different positions, and that would give you either pi over 4, 9 pi over 4, minus 7 pi over 4 going the other direction, that they're all kind of the same angle. So we'll need to remember the sine law and the cosine law. And we'll also need to remember a few sine identities. A good one is sine squared plus cos squared equals 1. That'll be one that we will probably use often to break things up and simplify. So now let's start looking at the graphs of sine x and cos x. And then we're going to estimate the instantaneous rate of change of each function at the given values of x. And then we're going to see kind of what happens and see what we get. Okay, I got to draw this with my finger on the screen, so it's not going to be pretty. So I'm going to pause this, and I'm going to try to graph y equals sine x and y equals cos x. Okay, so on one graph, I went ahead and just a quick sketch of cos and sine. And then I just want to look at kind of the instantaneous rate of change or the slope of tangent lines and kind of approximate them. So the easiest ones to do, let's look at the blue graph first, so your sine graph there. Now, looking at pi over 2, which is kind of the top, the maximum point there, I definitely know that my derivative, whenever I hit a maximum minimum, is going to be 0. So I could definitely go ahead and fill those zeros in right there. So as I reach this point up here, slope is definitely 0. As I reach the tangent down there, slope is definitely 0. And now looking at these other key spots here, maybe I should do it a different color. So kind of guessing the slope right along here and right along here kind of looks like a nice 45, kind of nice open slope. It kind of looks like it's a 1 there, and kind of looks like it's a -1 as I come down at pi. And then as I go back up there, it looks like I'm getting to a 1 again. Look at my derivative of sine, look at my cos. They're the same. Now let's look at the derivative of cos. So I can kind of again go with the maximum and minimum points. So I do know that when cos is 0, it's hitting a maximum. So I do know that my slope is going to be 0. And when I hit a minimum of the cos at pi, I know it's going to be a 0 slope. And then as I get over to 2 pi, cos has reached its maximum again. And I know the slope is going to be 0 because it's a maximum. We talked about kind of that relating the graph and the derivative graphs together. And if we hit a local maximum or minimum, we know that we're going to hit some zeros there. So I can kind of use that to fill those points in there. Okay, so now at pi over 2, let me find a color that's going to stand out here. Let's use this bright pink. I'm going to have my cos graph kind of goes down like that. So it kind of looks like a -1. And let's just switch colors again so you can kind of see what I'm doing. And then at 3 pi over 2, right about in there, kind of looks like it's hitting a +1. So it's not as strong of a relationship, but there's something there. Looking at the derivative of cos x and looking at sine x, when it's 0, it's 0. When it's 1, it's negative 1. Negative 1. Oh, it's just it's a flip. It's like a negative of it. So if I were to actually graph the slopes of my derivatives, I would actually get something pretty much the same. So I'm going to keep my light blue as my sine graphs. I'm just going to pause this as I draw my derivative graphs now. Okay, so I just did a quick sketch here of my two graphs. So I'll call that sine prime and like cos prime. So we can see that my sine prime is actually my cos graph. And then I can look at the derivative of cos. So cos prime is just the sine graph, but flipped upside down. So it's a negative sine graph. All right, so the derivative of sine and cos is not that bad. So here's my theorems that we discovered. If f at x equals sine x, then f prime at x equals cos x. Or if f at x equals cos x, then f prime at x equals negative sine x. And then if we want to have something a little bit more complicated, remember that we're really just using the chain rule again. So if we have f at x equals sine of g at x, then f prime at x equals cos of g at x. So I just change the sign to a cos, but then I times it by the derivative of what's inside. So it's a chain rule again. So, or the vice versa here, if f at x equals cos of g at x, then f prime at x equals, change it to sine, then times it by the derivative of what you're taking the sine of. Just remember that it's going to be the negative sign. So when we go from cos, it goes to negative sine. Sine goes to positive cos. So I changed the wording up just to remind you that we're not really doing anything different here. I asked you to find the instantaneous rate of change for any given point. What does that really mean? It means find the derivative. So we want to find the derivative of y equals cos 3x squared. So remember that my derivative, it says change it to minus sine, keeping everything the same, but then times it by the derivative of kind of what's inside the brackets. So the derivative of 3x squared is 6x. So I'll just write that a little bit nicer, and I'll write it as minus 6x sine of 3x squared. Awesome. There we go. So right away, I'm going to jump to one that's a little bit more involved. And we're going to have g at x equals the radical of sine x. First thing I'm going to want to do is just simplify g at x by writing that as sine, pardon me, my touchscreen is not working too great here. Let's try this again. Sine of x all to the 1/2. So if I want to take the derivative, g prime at x equals 2. So we're using that chain rule, bring the 1/2 down, keep the bracket as is, subtract 1 from the exponent, timesing it by the derivative of what's inside. So the derivative of sine x is cos x. So I can definitely simplify this. I want to get rid of my negative exponent, and then I can kind of just tidy things up a little bit here. So in the numerator, I'm going to have 1 and cos x. So I'm just going to have cos x in the numerator. The denominator, I'm going to have the 2. And then I'm going to have the square root of sine x. I could leave that as a fractional exponent if I wanted to. So just again remembering that the derivative of sine is cos, derivative of cos is negative sine. So let's look at one that goes a little bit more in depth. We got a bit of a product rule here. Yeah, we got power rules here. We got a little bit more advanced derivatives here, so this is definitely a good one. So let's take a look at this one here, and we need to find the derivative. So thinking again, kind of what do I have here? I've got, there's a kind of one term, is like my f at x. There's my second term, which is kind of like my g of x, and I'm going to have to use the product rule. It's kind of my main rule. Okay, so we got to remind ourselves that when we're using the product rule, I'm going to write it down this time. I won't always, but we're going to have f prime g plus f g prime. So that's the product rule I'm going with. So let's start by taking the derivative of sine of 5x. So I'm going to write down my y prime equals. So remember the derivative of sine is cos. So I write down the cos 5x. Then I times it by the derivative of 5x, which is 5. And then I need to times that by cos squared x squared plus 1. So that's just the first part of the equation. Then I'm going to add the f, so leave it as sine of 5x. Now, here's where it gets interesting a little bit. We have cos squared of x squared plus 1. So looking at that, this is really a chain rule. Like I got that exponent 2. So I need to bring that exponent 2 down, subtract 1 from my exponent, so now I'm just at regular cos of x squared plus 1, and then I times that by the derivative of what's inside. So the derivative of what's inside is 2x. Now I wrote that down and I'm seeing that I made a mistake. As I talk sometimes, as I'm trying to teach, sometimes I miss steps here. So I'm going to actually erase this, kind of go back over it, and I'm going to kind of rewrite it a little bit to kind of help me figure it out. So cos squared what I'm really doing is kind of like this. So we just don't write it like that. So I was kind of jumping ahead of myself here and I forgot to actually do everything here because it's kind of like a double chain rule. So I do bring that 2 down. Then I do write down cos, subtracting 1 from my exponent, so it's 1. Then I have x squared plus 1. But then I went ahead and just times it quickly by the bracket. But what's inside my bracket is that entire cos function. So then I got to times it by the derivative of the cos, which is going to be minus sine of x squared plus 1. So that's what the derivative of cos is. But then I have to times that by the derivative of what's inside the cos function, which is actually 2x. So that was a good one. I almost should have wrote that down in different colors as well, because I kind of have like a double chain rule. So the first part is, again, bring the exponent down in front, subtract 1 from the exponent. So I just have cos, and then I leave the x squared plus 1 as it is. And then kind of like anything to the power of 2, I kind of forget that squared out there, and I just take the derivative of cos. The derivative of cos says take it to minus sine, leaving the brackets aside alone, and then timesing it by what's inside. So the second part here, this is the derivative of just this part minus the exponent. The exponent is what I did over here. So kind of chain rule. So I did the chain rule first, bring the 2 down, and making it cos to the 1. Leave the brackets the same. Then what is the derivative of what's inside that brackets? Well, the derivative of cos is negative sine, and we leave the bracket as is, and we times it by the derivative of what's inside that kind of second set of brackets. So just have to slow down, and we can see we got this really crazy equation here. Okay, so the only thing I can really do with this now is maybe look to see if there's any coefficients or sorry, constants that we can bring together. So in this first term, so right now I'm just looking at how can I simplify this first term. I don't see much. So I can see that I do have a constant of 5, so I'll probably bring that out front. And then I don't really see anything, so I'm just going to write it down as cos of 5x times cos squared x squared plus 1. And that's kind of my whole first term. Not much I could do there. So let's find a different color. And now let's look at this entire second term, and let's see if there's anything I can do there. So inside those big brackets is all just 2 times this times this times this. So there's not really any terms in there, so I'm not really expanding. It's just all multiplication. So I can look for constants. I have a 2 in there, and I got a 2 at the end. I got an x in there, and just some crazy things. Oh, and I see a minus. So I'm going to actually bring out that minus that's inside the brackets, because it doesn't matter which way I multiply things. So I got the minus 1, and I got a 2 and a 2, so that's going to be minus 4. I can see an x, which I'll put right first, and then it's just a matter of writing down all my trig stuff next. So I'm just going to give myself some space here. It's just going to be the sine of 5x, and then the cos of x squared plus 1, and then the sine of x squared plus 1. Okay, shrinking it down. I don't think I can see anything. Oh, I do have a small common factor. I do have a cos of x squared plus 1 that I could take outside, but I don't have anything else. But I should be doing that as practice. So again, looking at this, I've got cos squared of x squared plus 1, and I have a cos x squared plus 1. So those are in common. So not that it's going to make things look any nicer, but to do it properly, I can common factor out a cos of x squared plus 1, and then I don't see anything else. So then it's going to be 5 cos of 5x cos of x squared plus 1 minus 4x sine of 5x. I took that cos out, so then just the sine of x squared plus 1. Okay, so did that make that look any nicer? Not really, but it is good practice. All right, let's look now at another one here. So we have h at x equals 3x squared minus 4x times cos 2x. Product rule again. So if I'm thinking about what I got here, I got 2 different things I need to take the derivative of. So it's the product rule, f prime g plus fg prime. So let's just get right to our derivative here. We'll have h prime at x is equal to the derivative of the first thing. So it's going to be 6x minus 4, leaving the cos 2x as is, plus leave my f as original, times the derivative of cos 2x, which is going to be minus sine 2x times the derivative of 2x, which is 2. So we can see again that I did do a product rule. So I had derivative of f, left f alone, left g alone, derivative of g. So I did just use a product rule. Now I can look to see if there's any way I could simplify this down and tiny little bit, that all I would do on the right hand side, I'm not going to write it all out, but I would take this 2 and this negative and I'd bring them outside. So I'd make this minus 2 3x squared minus 4x sine 2x. So that'd be a minor thing I could do. There's a common factor on the left-hand side I could do as well. Okay. So now, because this one's a little bit bigger, I'm going to pause it here in case anything goes wrong with the video, and then we'll come back and we'll try this one.